After studying this module, you shall be able to derive the rate constant on the basis of collision theory, know about the principles of collision theory. You will also learn about the effect of orientation of molecules on rate constant. You shall also be able to compare the rate constant as derived from collision theory with that of Arrhenius equation. In our previous discussion, we did discuss the relationship between rate constant and temperature as proposed by Arrhenius. In this module, we will take up in detail the collision theory of bimolecular reactions. Collision theory is a part of chemical dynamics and gives a quantitative account of reaction rates for the reactions taking place in gaseous phase. The collision theory explains how chemical reactions occur and why reaction rates differ for different reactions. This theory is based on kinetic theory of gases. Kinetic theory of gases assumes that all matter is made up of tiny particles called atoms or molecules which are in constant motion, and the temperature is a measure of average kinetic energy of the species participating in the reaction. On this basis, collision theory assumes that molecules are hard spheres and are impenetrable, that is, they can at most touch each other. The reaction may occur only when the molecules approach and collide with each other. Reaction occurs only if molecules are energetic, and collision should transfer certain minimum energy. Collision theory predicts the rate of the reaction based on two postulates. Number one, the product formation takes place only when the reactant molecules come close and collide with each other. And number second, only those collisions lead to the formation of products which satisfy the criteria of energy of activation and specific orientation of molecules. Now let us see how these factors affect the rate of a reaction. Let us consider the reaction in which the molecules are considered to be rigid, hard spheres with no forces of attraction or repulsion. For example, let us say A plus B gives the products. So for this reaction, the rate is expressed as ZAB into e to the power minus E naught by RT, where ZAB refers to the number of collisions that occur per unit time per unit volume. This is also referred to as collision density or collision frequency. So as per this equation, we can say that the rate of the bimolecular reaction depends on two factors. Number one, total collision frequency given by ZAB, and the Boltzmann factor given by the term e to the power minus E naught by RT. Now let us see how these two factors influence the rate of the reaction. Firstly, we will start with total collision frequency. The number of collisions per unit volume per unit time in such reactions is given by the expression ZAB equals to sigma under root 8 kT by pi mu into Na Nb, where sigma is the collision cross section and it represents the closeness of approach for the molecular collisions. Sigma is given as pi dAb square, where dAb is taken as the average of the diameters of the reactant molecules A and B respectively. Now this collision cross section of two molecules can be regarded as the area within which molecule A hits molecule B for collision to occur. The radius of contact of molecules A and B is given by dAb, which is the average that we have taken of the diameters of A and B. The other term in the expression is under root 8 kT by pi mu, which is the average energy of the molecules, where mu is the reduced mass, is given by the expression Ma into Mb upon Ma plus Mb. K is the Boltzmann constant, Ma is the mass of single molecule A, Mb is the mass of single molecule B. Na and Nb are the respective number densities of molecule A and B. Number density is given by the expression number of molecules upon unit volume. Now let us see what all factors influence collision frequency: temperature, concentration and surface area. Temperature: higher the temperature, more is the collision frequency and higher is the rate of the reaction. Concentration: particles that are packed more tightly together collide more frequently. Gases are more concentrated at higher pressure than at lower pressure, With increase in pressure, the concentration increases, which increases the collision frequency, and so the rate increases. And thirdly, surface area. Greater the surface area, more is the collision frequency, and so is the rate. Now, the other factor that influences rate of the reaction as per collision theory is Boltzmann factor. It is important to note that every collision does not lead to product formation. For the product formation to take place, the molecules should possess sufficient energy required for molecular rearrangement. This energy is not the kinetic energy of the two molecules, but it is the kinetic energy component of the relative velocity of the two molecules along the line of their centers at the time of collision. This is the energy of the two molecules with which they must be pressed together for the reaction to occur. Only those collisions which occur between molecules having energy equal or exceeding some critical energy E0, which as per Arrhenius equation is the activation energy, will lead to product formation, and such collisions which lead to product formation are called effective collisions. This energy should be equal to or greater than some minimum energy E0. The difference between the minimum energy and the average energy of the reacting molecules is the activation energy. The fraction of collisions in which the molecules have energy greater than the minimum energy E0 is given by Boltzmann expression, that is exponential minus E0 by RT. One should remember that the probability that a collision will occur successfully is incorporated by writing collision cross section as a function of kinetic energy of approach of two colliding entities and setting the kinetic energy 0 below a certain threshold value. Now with this, let us see how collision theory expresses the rate of a reaction. As per collision theory, the rate of the reaction is given by the expression as shown, which depends on collision density and exponential factor. Or one can simply say that the rate of the reaction depends on collision frequency and its probability of success, which is given by Boltzmann factor. Now for the reaction A plus B giving products, if we write rate in terms of decrease in concentration of the reactants, we express rate as minus dNA by dt, which is equal to K into Na into Nb as per rate law. And the concentration of A and B is expressed in the following manner. Concentration of A becomes equal to number density Na upon Avogadro's number, and the concentration of B becomes equal to number density of B upon Avogadro's number. So if we equate the rate with this equation, we get minus dNA upon dt equals to Na square K into concentration of A into concentration of B. Simplifying this equation gives us the expression minus d concentration A upon dt equals to Na K into concentration of A into concentration of B. Now substituting number density in terms of concentration in the rate expression given by collision theory, we get the expression as Na square sigma under root Kt upon pi mu into concentration A into concentration B into e to the power minus E0 by RT. Now if we compare this rate expression with the rate law expression, we obtain the expression for rate constant as K equals to Na into sigma under root 8 Kt upon pi mu into e to the power minus E0 by RT. It is important to mention over here that if every collision leads to formation of product, then the rate of the reaction will be entirely determined by the collision rate, that is frequency with which reactants collide. Thus, it gives the maximum rate that can be observed experimentally for the reaction, or one can say this provides the upper limit or limiting value to the rate constant. Now, if we look at the microscopic level, if we have two reactants, then they can only react if they come into contact with each other, that is if they collide. Then they may react or they may not react. Collision alone is not enough. They must collide the right way. They must have enough energy for the bonds to break. Even if the collisions happen the right way, the reaction will not occur unless the particles collide with a certain minimum energy, that is the activation energy. If the particles collide with less energy than activation energy, they will simply bounce and no reaction will occur. So activation energy acts like a barrier that has to be crossed for the reaction to occur. another factor that comes into picture is the collision must occur the right way. That is the effect of orientation of molecules on the rate of the reaction. Although there is some energy requirement for effective molecular collisions, the reaction occurs only when the molecules have proper orientation. Only those collisions taking place between molecules in proper orientation and possessing certain minimum energy lead to formation of products. Thus, it is important to study the effect of orientation of molecules on the rate of the reaction. Now, to study the effect of orientation of molecules, we have considered a reaction involving ethene and hydrogen chloride, that is CH2 plus HCl giving CH3 CH2Cl chloroethane. As a result of collision, the double bond between two carbon atoms of ethene is converted into a single bond, and a hydrogen gets attached to one of the carbons and a chlorine gets attached to the other. It is important to realize that this collision or this reaction will only occur if hydrogen end of HCl bond, hydrogen chloride bond, approaches the carbon-carbon double bond. Any other collision between the two molecules will not work. As we can see in the diagram, the four collisions are represented between ethene and HCl. As can be seen, collision 1 is the only effective collision which results in product formation, whereas collision 2, 3 and 4, because of incorrect orientation, do not lead to the desired result. Thus, we conclude that the rate of formation of products is not only dependent on collision energy, but also on relative orientation of the molecules at the time of collision. Thus, the reacting species must have proper spatial orientation for the reaction to occur. This criteria of specific orientation of molecules at the time of collision is taken into account by multiplying factor P in the rate constant expression as obtained for collision theory. This factor or constant P is the steric factor and is usually less than unity. So with this, we have the complete expression for rate constant as obtained from collision theory. Now, let us compare the rate expression that we have obtained from collision theory with that of Arrhenius equation. We did discuss Arrhenius equation in our earlier module, where the rate constant is expressed as K equals to A into e to the power minus Ea by RT, where Ea is the activation energy and A is the pre-exponential factor. And as per collision theory, the rate constant is given by the expression K equals to P into Na into sigma into under root 8 kt upon pi mu into e to the power minus E naught by RT. We can simplify the rate constant expression as obtained from collision theory as K equals to B into under root T into e to the power minus E naught by RT, where we have assumed B as P into Na into sigma into under root 8 K upon pi mu. So, we can say that B is constant and is independent of temperature. Now, both these equations, Arrhenius equation and collision theory equation, relate rate constant of a reaction to various factors. Let us consider Arrhenius equation. Applying logarithm to both the sides gives us the expression log K equals to log A minus Ea by RT. And if we differentiate this expression with respect to temperature, we get del log K upon del T equals to Ea upon RT square, where A is assumed to be independent of temperature. Now, let us look at the collision theory expression. Again, if we apply logarithm to both the sides, we get the expression as log K equals to log B plus 1 by 2 log T minus E naught by RT. If we differentiate this expression with respect to temperature, we get del log K upon del T equals to 1 upon 2T plus E naught by RT square. Now, comparing the equations as obtained from Arrhenius equation and collision theory gives us the expression Ea upon RT square equals to 1 upon 2T plus E naught upon RT square, which simplifies to the form Ea equals to E naught plus RT by 2, where E naught is the energy barrier as defined by collision theory leading to formation of products, and Ea is the activation energy as per Arrhenius equation. So, as can be seen, E naught is not exactly same as Ea. Thus, from the above relation, we find that activation energy is dependent on temperature. Now, when we substitute the value of E naught in terms of Ea and temperature, In the collision theory rate constant expression, we get K equals to B under root T e to the power Ea minus RT by 2 upon RT. Simplifying this expression gives us K as B into under root T into e to the power half into e to the power minus Ea by RT. Now, if we compare this rate expression with that of Arrhenius equation, we find that the pre-exponential factor comes out to be B into under root T into e to the power half. Substituting back the value of B gives us the expression for A as P into Na into sigma under root 8 kT upon pi mu into e to the power half. As per this theory, we find that value of A is temperature dependent. So we can say that A is the correction term which compensates for collisions with non-productive molecular orientations. In all, this theory is qualitatively consistent with the observation, that is Arrhenius equation. No doubt, this theory provides a plausible connection between microscopic molecular properties and macroscopic reaction rates. However, collision theory cannot account for reversibility. Now let us summarize this module. In this module, we discussed about collision theory of bimolecular reactions in gas phase. We did discuss that this theory is based on kinetic theory of gases and predicts the rate of the reaction based on two postulates. Number one, the product formation takes place when reactant molecules come close and collide with each other. And number second, only those collisions lead to formation of product which satisfy the criteria of energy of activation and specific orientation of the molecules. The expression that we obtained for rate constant from collision theory is of the form K equals to P into Na into sigma under root 8 kT upon pi mu e to the power minus E naught by RT, where P is the steric factor, sigma is the collision cross section, under root 8 kT upon pi mu is the average velocity of molecules, and e to the power minus E naught by RT refers to the Boltzmann factor. From this, we obtained that the rate depends upon collision frequency, its probability of success as given by Boltzmann factor, and relative orientation of the molecules given by the steric factor at the time of collision. This theory provides in all a plausible connection between microscopic molecular properties and macroscopic reaction rates. With this, in the next module, we will take up activated complex theory in detail.